Okay, today we're going to do approximating area, and we'll cover two different types of approximations of that area, the trapezoidal rule and Simpson's rule, and then we'll go ahead and have a look at surface areas of geometric figures and volumes of geometric figures, and the sine rule and the cosine rule. Alright, so let's begin with the trapezoidal rule. So suppose we have a two-dimensional shape with four sides. So you can have a look at figure 14 there. What we see is a trapezoid. Now on one side we've got parallel edges that are opposite, and then this base is perpendicular, and then we've got some slant there. So that's a trapezoid. So what we're going to do is use this to approximate the area under a curve between 2 points, say A and B. Okay, so what we do now is we approximate the area of this by saying that it's the length of the base times the average height. Okay, however, this is exact in this figure because that is in fact the area of that trapezoid. Right? But it makes a good approximation when we have, say, a curve between here and here, right, of the area under that curve. Okay, now this little calculation at the bottom shows us that this area is actually equal to h on 2 b1, which is the height of this, plus b2. So what we have then is a is equal to h times b2. So if we take that, calculate the area of this rectangle, and then the second part of this is the area of that triangle, which is a half the height times the base, but the well, I guess it's the h is the base and this would be the height, but you could turn it the other way around. So b1 minus b2 is this little length here. So this times this divided by 2 gives you the area of this little triangle. So you see this formula is accurate for the area of this trapezoid, but if you factorize the h out and simplify, so let's just go ahead and do that here, factorizing the h out of the front, we've got b2 plus 1/2 b1 minus 1/2 b2, and then b2 minus 1/2 b2 is 1/2 b2, and then you can factorize the half out, and you have h on 2 in brackets b1 plus b2, which explains the trapezoid's connection to the area under this curve used as an approximation, right? Because what this is it's the average of these two, which would be somewhere in here, and then multiplied by this, right? So we approximate the area under the curve, which would be this part of it, by the average between this and this, multiplied by that h value. Okay, let's move on to the next page. So to estimate the area under the curve, let's have a look at figure 15. We break up some region, so suppose it's from here to say here, and we would break this up into rectangles of equal width whose height is the average of this point to this point. However, you could connect those and make some trapezoids, right, which explains the naming of this. So if we were to calculate the area under a given curve, we would usually use calculus, a technique called integration, but there are some examples of this where it's not so simple, or the formula that you get using integration is not so readily useful. So for example, the area under the curve y is equal to e to the power of minus x squared, where e is the base of the natural logarithm, 2.718281828, and then the numbers are different after that. So this curve, and it looks like this, right? It has a peak up here when x is 0 of 1, but it's the integral of this doesn't have a simple formula like something like sine, cos, polynomial, or other. It's actually in terms of the error function. And so people would calculate the error function using tables. However, the trapezoidal rule and Simpson's rule allow us to estimate the area under such a curve without any fancy functions. Okay, and it's useful to be able to calculate the area under this curve because it relates directly to probabilities. Okay, so now to compute the area, we would divide the interval from a to b into n equal subintervals of width h. So h would be x subscript I minus x subscript I minus 1. So let's go ahead and look at the diagram where we do that. So here we've got some really tiny intervals, and it looks like they are of width 0.1. 0.1 is the width of these. And so what we're doing is we're putting little rectangles here, and we're estimating the area between here and here using an average height and a width of 0.1, for example. But you could choose any h value, presumably less than 1. To do that, you need it less than 1 to get a good estimate. And so then we add up all of the rectangles, much like what you see here in this diagram. So we add up the area of all of those rectangles, and we take that to be a reasonable approximation of the area under the curve. Alright, so here's some mathematics, but I'm going to rewrite this so we can discuss it along the way. So, and it'll be a little bit bigger as well. So A is approximately, we have h on 2, but this is h times f of x1 plus f of x2. Now f of x1 is the height of this function at the point x1. F of x2 is the height of this function at the point x2. So this is the average height times the width. And then we're going to add on the next little rectangle. So if we start here on the left, our next one moves to the right slightly. So for that we have h on 2 f of x2 plus f of x1, or x3. And then we continue in this pattern, so the next one after that would be h over 2 f of x3 plus f of x4. Again, this is the height of the function when x is x4. and so on. So plus dot dot dot, and then the last one at the end would be h on 2 f of x n minus 1 plus f of xn. Okay, now you can see that we have an x2 here and we have an x2 here. So if we were to expand, or first say factorize the h on 2 out and then look at what we have remaining inside the expanded bracket. So what we have then is, pulling the h on 2 out of every term, we've got 1 of the fx1s, but then we have 2 of the f of x2s, and we have 2 of the f of x3s, and in fact we have 2 of all of them except for the last one, f of xn, and the first one. So 2 f xn minus 1 plus f xn. Okay, great. So next we want to express this in a special way. So if we say let a1 be equal to f of x1, now I hope that's what I've done here, yes. Okay, let a2 be equal to f of x2, and so on, an be equal to f of xn, then what we're saying is a is approximately h on 2 times the sum a1 plus 2 a2 plus 2 a3 and so on just like this. Right, so we have a coefficient of 2 in front of all the heights of the function that are not a1 and an. In other words, not the first and not the last. Okay, so given that, can we express this using a matrix multiplication? And the answer is yes. Right, because we can write this as h on 2, that's a scalar, times the matrix 1, 2, 2, 2, dot, 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 2, 2, 1, etc., multiplied by the column a1, a2, a3, dot, 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 up to an. Okay, now if you multiply this out, remember this goes with this, this goes with this, this goes with this, and so on, and then you add the result, so you actually have the same thing as this. Alright, now notice that the data occurs here, so this is all the data, and then these are all of the coefficients, and then this is h on 2 there. So it's convenient to use it this way. And especially if you're using both the trapezoidal rule and Simpson's rule together and comparing the results, you can even put the corresponding array for Simpson's rule below this and have the data there once, and you get both just by doing a matrix multiplication. Alright, let's move on to the next page. So this is exactly what we've done just there. Now let's have a look at an example. 9.1. Use the matrix form of the trapezoidal rule to estimate the area under the curve y equals sine of x from 0 to 1.8 using 7 points and a step size of 0.3. Alright, so let's just make a little sketch of this sine wave. Now this would be in radians, okay, so sine starts at 0, crosses at pi, which is approximately 3.14, and then it returns at 2 pi, so something around 6.28 or so, and then this right here would be pi on 2. Now that's probably, I'm guessing, about 1.57 if I remember right. Okay, now 1.8 would be, say, somewhere in here. So we want to estimate this area from 0 to 1.8 using 7 points and a step size of 0.3. All right, so let's carefully set this out. So here we'd have 0.3. All right, so we take the average height as our height of the rectangle, so somewhere in there. And then the next one would be 0.6. And I see I've drawn this too wide to fit in properly. Okay, so we're taking the average height here, so 0.6 is probably much closer then, right? So, maybe we'd put it in here, 0.6, and then 0.9 goes there, and then, say 1.2, and then 1.5, and then 1.8. So, since I've kind of stuffed up my drawing there, I'll draw just the base so we can carefully think about it, right? Your drawing doesn't have to be perfect. All right, now 18 divided by 3 is 6, so I want to divide this into 6 portions. Okay, now let's see if that works out. 0.3, 0.6, 0.9, 1, is that correct? 1.2, 1.5, and 1.8. Okay, so we've got 6 segments. So 1, 2, 3, 4, 5, 6, but n is 7. So this would be n equals 1 right there. N equals 2 corresponds to this. N equals 3 to that. N equals 4 to that. N equals 5, this one. N equals 6 here, and n equals 7 there, right? And let's see if I can improve that sketch. So 1.57 would be, say, in here. So we'd be coming, up something like that. Right, and we want to estimate with rectangles of average height between here and here. Okay, great. So what we need to do then is estimate sine of 0, which of course is 0, sine of 0.3 radians. So we need our array of data, A1, A2, A3, A4, A5, A6, and A7. Right, now this is sine of 0, which is 0, sine of 0.3, and so on. And then the last one here is sine of 1.8. All right, now my previous calculations gave me these numbers. And so now what we need to do is multiply that on the left by this matrix in order to use the trapezoidal rule to get our estimate of the area under the curve. Okay, so 0.15 is 0.3 divided by 2. And then here's our matrix of coefficients. Here's our data. So we multiply this by this. Remember that requires a sum. And I get 1.21798 and so on as the area under the curve from 0 to 1.8. So if you know calculus, you might have done Math 104, then this is approximately the integral from 0 to 1.8 of sine of x, just like that, right? If you have done calculus already. All right, so let's move on and look at another rule. So a slightly better rule because you get more accuracy, as in the error is less in the approximation. So that's Simpson's rule. It approximates the area under the curve with more accuracy in general than the trapezoidal rule, and estimates the area under the curve as this. But let's write something out by hand here. So it estimates the area under the curve from x1 to x3, and in the middle, let's say there's x2. So it takes in 3 points. And estimates this area as h on 3 f of x1 plus 4 times f of x2 plus f of x3. Okay, so now doing this over several, we have this is the first one, then this is the second one, plus dot dot dot, this is the nth one. Okay, now we need to assume though that n is odd to make this work, and h is the distance between the consecutive xi, so this in here would be our h distance. Okay, so factorizing the h on 3 out, or expanding and replacing the f of x1 with a1, f of x2 with a2, and so on. This is what we have, and then we want to factorize out the h on 3. And so we can represent that with this nice little matrix formula where here on the left we have the data, or sorry, on the right we have the data, and on the left we have the coefficients, and then in the front we have the scalar multiple h on 3. Okay, so just to look at an example, much like what we did in the last one, but using Simpson's rule, here we have our data, just as before, and then if we multiply on the left by this matrix, we should get hopefully a better estimate of the area under that curve. All right, so this product, so h, remember, was 0.3, so 0.3 over 3 is 0.1, and we get 1.22726, whereas before we got 1.12798 as an estimate. So this should be a better estimate. So the actual area under the curve, y equals sine x from 0 to 1.8, is 1.22720. So this is quite a bit better than 1.21798. Alright, so in our next section, we can use this to approximate the area of a lake where a surveyor might set up a laser here at one end and then measure across to a reflector over there, for example, and get a distance. And if you do this equally distant apart, then you can use Simpson's rule to get a good estimate of the area of that lake. So if these are those calculations, then we can put that into a matrix. So this is the matrix for the trapezoidal rule. So that's half of the width, which is 26 over 2, presumably kilometers. Yeah, kilometers. Here's our matrix of coefficients. Here's our data of the lengths across the lake. And so we multiply this out and we get 19,500 square kilometers as the lake area of Lake Ontario. So it's known to be 18,960. So that's actually not too bad, given that these were taken 26 kilometers apart, these measurements. Okay, so next example, a cartographer determines the width of Easter Island at 1.5 kilometer intervals as follows. So here's Easter Island. The widths of these measurements are 1.5 kilometers. And so here's our data. So we put that data into this column matrix. This is the matrix of coefficients for Simpson's rule. 1.5 over 3, that's the number out the front. So we multiply this by this data matrix, and we get 173.55 square kilometers as the approximated area of Easter Island. But it's known to be 163.6 square kilometers, so not too bad. So not too far off. Okay, 9.4. Radians and the area of a sector of a circle. There are 360 degrees in a full circle, but we can also measure with radians. See figure 24. Let's have a look. Well, it's probably this figure. So what we have here, now we'll just describe this in the way that I sometimes think about this. So we've got a circle of radius r, and suppose this is 1 radian there. Okay, so this is like we have an equilateral triangle here, and then what we do is we pull out, and that would bring these sides in just a little bit. So we pull it out so that it fits the edge of the circle. Okay, so now we started at 60 degrees, which is the interior angle of the equilateral triangle, and we made it just a little bit smaller by pulling it out until it matches. So 1 radian is defined as the angle required so that we have an equal side there as to there, but that's inside a circle, so that's true. And the distance along this arc is equal to the radius, and so that's 1 radian. So what we're going to do is learn to convert between radians and degrees, and to use radians where appropriate. So they're more natural, arguably, than degrees. For example, this identity due to Euler, e to the pi I, where I is the square root of -1, is cos of pi plus I sine of pi. Okay, so when you take theta being equal to pi, this identity says that e to the power of pi I is minus 1. And you can rewrite that just like this, and it's said to be one of the most beautiful identities in mathematics. But this only works in radians, right? So like that would not be true if you calculated e to the power of 180 I and then plus 1, right? So you would not get 0. So this relationship works in radians, and so that's why I say it's arguably more natural than degrees. Okay, so in this section we'll consider the relationship between an angle, the arc lengths of sectors, and the area of the sector. 1 radian is defined as the angle such that the sides of a sector with angle 1 radian are, and the lengths of the sides are equal. So in degrees this should be slightly less than the interior angles of an equilateral triangle. So I think from memory it's around 57 degrees or so is 1 radian. Since the circumference of the circle is 2 pi r, there are 2 pi radians in a sector that covers the full circle. So all the way around would be 2 pi radians, which we know is 360 degrees. And that there should say 360 degrees, not 260 degrees. Hence we have the angle unit conversion, 2 pi radians equals 360 degrees. In order to convert between radians and degrees, we can express this relationship as 1 is equal to pi over 180 degrees, or pi radians over 180 degrees, and conversely, if you want to translate from radians to degrees, then you would multiply by this form of it, which is that 1 is equal to 180 degrees over pi radians. Okay, for example, to convert 30 degrees to radians, we multiply by 1 using one of these, right, so that the degrees units cancels. So that would be this one. We'd multiply by pi over 180 degrees so that the degree unit would cancel. And so that would be pi on 6 radians. Okay, but here is the way the calculation works. 30 degrees is 30 degrees times 1, which is 30 degrees times pi radians over 180 degrees. And so 30 over 180 is 3 over 18, which is 1 over 6, because 18 is 3 times 6. Now to convert radians to degrees, we would multiply by 180 degrees over pi radians. For example, 7 pi on 15 radians is equal to 7 pi on 15 times 180 degrees on pi. And so we can cancel the pi in the numerator and the denominator. Now 180 would be divisible by 15. So we represent this as 7 times 180 over 15. And so what is that? If we multiply top and bottom by 2, then we have 360 over 30, which is 36 over 3. So 7 times 12 is 84 degrees. When the angle theta in the figure is measured in radians, and the following identity includes those given in equation 20 above. Okay, so what we had then is that, let's have a look at the figure again. So this angle theta gives you a proportion of the angle 2 pi radians. So what I should say is that theta over 2 pi is s over the whole circumference of the circle, 2 pi r. Okay, now if we multiply left and right by 2 pi, we get this identity right here. And if we rearrange that, then we get s, the length across here, is equal to theta r. So s is theta r, which is what we have there in equation 22. So similarly, we can calculate the area of a sector. Now the area of the circle is pi r squared. The area of the sector through an angle theta is a fraction, theta on 2 pi, of that, given by theta on 2 pi of pi r squared. And we cancel the pi and we get 1/2 theta r squared for the area of the sector. Okay, let's have a look at example 9.5. What is the arc length and the area of a sector that makes an angle of 1.7172 radians and has a radius of 2.70 meters? Okay, so we want to use our equation for the arc length of that sector, which is theta r. So we said we've got 1.7172 radians, and then r is 2.70 meters, so we just take the product of those, and so we find that the arc length is 4.63644 meters. With 3 significant figures, we could report that report an arc length of, and that should say 4.64 meters. To calculate the area, we use equation 24, which is that the area of the sector is equal to 1/2 theta r squared, which we have right here. So 1/2 times 1.7172, which was the angle, times 2.70 squared, and we get 6.259194. If we were to represent that with 2 significant figures, then we would write 6.26 meters squared for the area of the sector. Okay, next, the cosine and the sine rules. So I'll give a little proof of this. Consider the following diagram in figure 19, so that's here, which shows 3 vectors v1, v2, and v3, where v3 is the sum of v1 and v2. Okay, now the side lengths of the triangle that we see there, let's call this side A, this side B, and this side C, which are the norms of each of those vectors. So let's derive the cosine rule from this. So c squared is the norm of v3 squared. So the norm of this length, the norm of that vector is the length of that triangle side. Now there's an identity that says the square of the norm is v dot v, right? So the square of the norm of v is v dot v. So this is v3 dot v3. Now we said that v3 is v1 plus v2, so we can substitute that in there, and now we can expand that dot product to get 4 dot products added together. So v1 with v1, so that's v1 dot v1 plus v1 dot v2 plus v2 dot v1 plus v2 dot v2. Okay, now v1 dot v2 is equal to v2 dot v1, so we've got 2 of these. v1 dot v1 is the norm of v1 squared. v2 dot v2 is the norm of v2 squared. Now there's an identity that says that v1 dot v2 is the product of the norms cos of the angle between them, but actually the angle between these, because I've got the, I don't have them tail to tail when I measure the angle, right? So I should actually, let's call it theta there. Right, so it's like this. So I actually should not have plus here, I should have minus. Which is a little typo. Okay, now in the next step, and that should be here as well, but in the next step we make the observation that V1, the norm of V1 is A, so this is A squared, this is minus 2AB cos of C, and then this, the norm of V2 is B. So that's B squared. Alright, so what we have then is this identity C squared is equal to A squared plus B squared minus 2AB cos of C, which is our next equation. Equation 25. And this is called the cosine rule. It generalizes Pythagoras' theorem because if C were 90 degrees, then cos of 90 degrees is 0, so we would get A squared plus B squared equals C squared. Okay, next up, the sine rule can be constructed similarly using the identity for the cross product. So we've got this identity for the norm of the cross product. The norm of V1 cross V2 is the product of the norms sine of the angle between them. And again, we would have to take that angle between them as theta. Alright, so V3 is V1 plus V2, so we have the cross product of, or the norm of the cross product of V2 and V3 equals the norm of V2 cross V1 plus V2. Okay, now we expand that cross product. The cross product of these two gives us V2 cross V1 plus V2 cross V2. Now, the cross product of a vector that is parallel to another vector must be 0. And so, of course, V2 is parallel to V2, so we get 0 for that. So this is just the norm of V2 cross V1. Now, using the formula 26 here, we see that that is the product of the norms sine of A and the product of the norms sine of C. So, assuming that the norm of V2 is non-zero, we can cancel that on both sides, and we get the norm of V3 sine A is the norm of V1 sine C. And since A, which is the norm of V1, is non-zero, and we're assuming that the norm of V3, which is C, is non-zero, we get this, which is the sine rule. And so similarly, we can extend this to the following identity in equation 27. A over sine A is B over sine B, which is C over sine C. Okay, but we need to take a little bit of care because in using the sine rule, sine of theta is the same as sine of 180 minus theta. Alright, so let's draw a little diagram here. So this diagram that says that sine is positive here and it's positive here, right? So this is theta, this is 180 minus theta, where this is the angle theta from the negative end of the x-axis to this little line here that's symmetric about the y-axis there. Okay, so that's why we have that identity. It's also helpful to note that when solving triangles that the sum of the interior angles of a triangle add up to 180. So you can use this identity to discard some of the answers you might get when you're taking an inverse sine. All right, let's have a look at the following example. Assume that we have a triangle with sides 10, 12, and the angle opposite A is 35 degrees. Determine the remaining side A and angles B and C. All right, so let's use the cosine rule. So we have A squared is 10 squared plus 12 squared minus 2 times 10 times 12 cos of 35 degrees. Simplifying this, we have 244 minus 240 cos 35. Now cos 35 gives us 0.819152, and so we simplify this and get A squared is 47.4035 and so on. Taking the square root gives us that the side A is 6.885. Now to find angle B, we use that part of the sine rule given by this. B over sine B is A over sine A, where the angle A is opposite the side A and the angle B is opposite the side B. Okay, so let's have a look. It follows this sine B is B sine A over A. So right there. So we sub the numbers in and we work out that sine of B is 0.833081. So taking the inverse sine of this, on your calculator that's sine superscript minus 1, but I like to call that arcsine. So we get two answers for that, right, because of this diagram here. Sine is positive in the first and the second quadrant. So we've got 56.4 degrees or 180 minus that, which is 123 degrees, 0.58. But since the given triangle has angle B, it must be less than 90 degrees because A plus B plus C is 180 degrees. So we have to have that this angle is 56.4166 degrees, not 123.583 degrees. Okay, finally from that, we can work out our third angle. C is 180 minus A minus B, and we get 88.5834 degrees. Okay, so we now have all side lengths and we have all interior angles.